first lesson of Unit 2. So Unit 2 is going to be all about limits. We're going to cover 6 different lessons in the textbook. We're skipping a few just because of time in the course and topics that I want to cover. Okay, so we're going to start with 2.2, which is limits of a function. So we're going to define what a limit is today. That's going to be the topic of the entire unit. And then we're going to practice evaluating some limits using graphs and also tables. Okay, so what is a limit? What are we going to be studying for the next couple of weeks? So a limit is a value of a function that a function approaches as the x value gets closer and closer to a number. Okay, so the limit is the value that a function. So notice I'm not saying the limit is a value that a function is equal to. It's the value that a function approaches as x gets closer and closer to a number. So the way that we denote this in math is we say limit LIM. I like to use it's common to use a cursive L to the L, so LIM, and then you write the function f of x, and you need to say what x value you're getting closer and closer to. So we say x approaches and then a. That a could be anything. It could be the number 2, 3, 4, -5. It could even be infinity, actually. Okay, and this is going to have an answer, so I'll just put b. Okay, so we're going to do an example now for a rational function. Let's look at this function here. So here our function is x minus 3 over x squared minus 4x plus 3. And let's pretend we don't have the graph of this. We're just interested in some values of this function. And let's say we start plugging in using your calculator. So I'm going to write this over here. So x minus 3 over x squared minus 4x plus 3. Let's try to plug in f of 3. So we get 3 minus 3 over 3 squared minus 4 times 3 plus 3. And what we would find out is that we get 0 over 0, which is undefined. So if I was trying to graph this function, I would have no idea what to do around the point f of 3. So, but I still want to know what's going on. So that's when a limit becomes really useful, because we can see what's happening to this function very close to 3 and see what this function is approaching as we get closer and closer to 3, but not actually at the point 3, because that's undefined. So let's use a table to do this. So when you make a table, we need to approach this value 3 from the left and the right. So I'm going to say from the left here and from the right. So what I mean by the left is values that are a little bit less than 3 and getting closer and closer on that side. And then on the right means values that are greater than 3, but getting closer and closer from the right side. So values that get closer and closer to 3, you can pick whatever numbers you like, as long as they're getting closer to 3, but I like to just go like 2.9, 2.99, 2.999, 2.9999. I think I'm only going to do 3, because by the time we do those 3, you're going to see what the answer is. And then the values that are a little bit greater than 3, you could start with 3.1, and getting closer to 3, you could do 3.01, 3.001. Okay, and then you're going to plug these values into your calculator. So this part's a little bit tedious. I've already done it for you. So I'm just going to write the answers down. So when you plug in 2.9 into the function, it is defined. It's not 0 over 0, so you get an actual answer. 0.5263. And when you plug in 2.99, you get 0.5025. And the next one is 0.5003. These are all rounded off, they're longer decimals. So maybe the function's approaching 0.5. Looks like it might be. Let's do the other side and see. So on this side, if you plug in 3.1, we get 0.4762, 0.4975, and 0.4998. So definitely getting closer and closer on both sides to 0.5. So what we can say now is the answer to this limit is 0.5 or 1 over 2. In words under here, we're going to write this down. So we're going to say the limit as x goes to 3 of this function f of x equals 0.5. So in words, we'd say the function approaches, it's not equal to 0.5 because remember at 3 it's undefined, but it approaches 0.5 as x approaches 3. What does the graph look like? Let's look at the graph. So here is the graph of the function. This is f of x. Okay, and let's zoom in. Just going to highlight here around x equals 3. So notice that the function is approaching 0.5, and at 3, there's a hole in the graph. So if you've done pre-calc 12, you'll know that hole means it's undefined at that point, but the limit tells us a little bit more. It says, basically tells you where the hole is. I'm saying the function from both sides is approaching 0.5, but at 3, not necessarily defined. Sometimes the limit value is equal to the function value at that point. In this case, that's not the case. Okay, so that's a case where the limit is equal to an actual number. Sometimes the limit's going to equal to infinity or negative infinity. So these are called infinite limits, and these happen usually where you have asymptotes. So some functions take off in the positive or negative direction as x approaches a value. And in that case, what we say is, I don't have space here, but I'll write it here. And the limit as x goes to a of the function is infinity, or it could be negative infinity. And again here, the function would not be defined at this point, but you can still, the limit gives you more information about the function than just being undefined. So here in example 2, we have the function f of x equals 1 over x plus 2 squared. And let's say we're interested in this point, negative 2. It's not part of the function. It's not part of the domain. So when you plug in negative 2, you get 1 over 0, so it's undefined. But let's say you still wanted to graph this function, and you want to know what's going on near that point, at x equals negative 2. So that's where the limit's going to come in handy. So I'll show you what it looks like to be an infinite limit. So we're going to approach negative 2. Now I'm going to split this table in half. We're going to go from the left and the right. So we'll start with values a little bit less than negative 2. So like negative 2.1, negative 2.01, negative 2.001, and then values a little bit greater than 2, negative 2. So like negative 1.9, negative 1.99, 1.999. So again, a little bit tedious to plug in. Later in the unit, we're going to have other methods to solve these limits. But for now, you just need to plug in your calculator. And I've already done it for you. So when you plug in negative 2.1, it actually comes out as a nice number. It's 100. And then it's 10,000. And then it's 1,000,000. 6 zeros, 1, 2, 3, 4, 5, 6. Because it's squared, it's an even function, so it's actually kind of symmetric a little bit. Or it's not an even function, but the squared makes it the same on either side of negative 2. So these actually give you the same values. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. So you can see the function is growing and growing and growing. It's taking off in a sense. towards positive infinity as these x values approach -2. So what we can say is that the limit is equal to infinity. When that happens, that means you have an asymptote in your graph. That means the graph is approaching infinity on either side of -2. And so I'm just going to label this here. So in red, this is the graph. In red here, we see this vertical line. This is a vertical asymptote at x equals -2. Okay, and you can see the graph as it approaches -2, it's approaching infinity on both sides. Okay. So limits, again, they can equal a number, like in the first example, or they can equal infinity. And they're useful, especially at points where the graph is undefined. They give you more information about the graph. Okay. Sometimes limits are, so notice we've been splitting our table into left and right. Sometimes the limit on the left and the right are not equal to each other. So we're going to look at that case next. So this got cut off. It was supposed to be on the next page. So left-handed and right-handed limits. So if you want to specifically look at what's happening as x approaches a certain value from the left side only, you use this little negative sign, and it's not, doesn't mean negative, it just means from the left. So when you put the negative sign sort of up above and to the left of the number, it means approaching a from the left-hand side. And when you use a plus sign here, it means x approaches from the right. Okay, so you can specify if you want to look at from the left or from the right. When those numbers don't equal each other, so far the examples we've seen, they have been the same in our tables, but sometimes they're not going to be equal. And in that case, we say we can specify what they are, but the actual limit itself, if you don't have any specification from left or right, we say the limit does not exist because it's different on the left hand and the right hand side. So you can't give one value is not more important than the other. So the limit itself does not exist. However, you can say the left hand limit equals this and the right hand limit equals this. Okay, so let's do an example with a graph this time, no table anymore. We have this piecewise function g of x here. We have a jump right here. So the function is not defined at x equals 2. And at x equals 5, there's a hole in the graph, but we do see a colored in circle here at 5. So the function is defined at x equals 5. I'm just going to write down here, so note, let's see what's going on. Just going to write, because we're not really used to these piecewise functions. G of 2 is undefined. Because if one of these was colored in, then it would be that value. But since both are open circles, that means it's undefined at x equals 2. And g of 5 is, so wherever the colored in circle, that's what the value of the function is. So g of 5 is equal to 1. Okay. Let's look at the limits though. So A, the limit of g of x as x approaches 2 from the left. So this means left side. So I'm going to approach 2, so I'm going to follow the function and look from the left side only. I don't care about this part of the function. And we see that it approaches the y value of 3. So the limit from the left of g of x is 3. Let's approach 2 from the right side. So I'm going to go to the right side of x equals 2. I'm going to follow the function, and we see that it approaches a y value of 1. Okay. So the left hand and right hand limit as x approaches 2 are different. From the left, the function is approaching 3. It's not defined at 3, but it approaches a value of 3. And then from the right side, it approaches a value of 1. So if you're going to ask what the limit of g of x as x approaches 2, it's different from the left and the right. So we would say the limit is undefined, or it does not, oops, whoa, what's going on there? Don't know why that happened. Does not exist. So you can write D and E for short. Okay, let's look at the limit as x approaches 5. So from the left side, I'm going to do that same thing. From the left side, we see that the function approaches a y value of 2. Okay, notice that the colored circle doesn't actually matter. You're just following the function as we're approaching 5, not at 5. And then from the right, it's also equal to 2. So the left-hand and right-hand limits in this case are the same. And so the entire limit does exist because the right and left are equal, and it would equal 2. Okay, so in this case, the limit is different from the value of the function. Okay, so you should be able to draw, if I said, draw a function where the limit at x equals 2 or x equals 5, for example, is different from the value of the function at that point, this is the kind of picture that you could draw. So that's a case where the limit value is different from the function value. So usually that's a case where you have a hole in the graph and then the colored in point somewhere else. So the function's approaching a certain value, but then the actual value at that point is different. Okay, well, that's the end of this lesson. So your assignment is going to be just to evaluate lots of limits using tables and graphs. And then next lesson, we're going to be evaluating limits algebraically.